In this video, I'd like to talk about the thought experiments of Carnot. In particular, I'm going to focus on the Carnot cycle for power generation. Carnot's reasoning can also be applied to things like refrigerators and heat pumps, but I'll discuss that in subsequent videos. Right now, the problem that I want to discuss is, let's say I have some sort of liquid, could be water and steam, and I want to apply heat. For example, I could burn coal, and I could produce a high temperature and pressure gas. Which could be steam. I could run that steam through a machine and produce work, and somehow the byproduct of that would be a low pressure and temperature gas, which I could then recycle back into the original state as a liquid by removing the heat. Now, the idea here is that by moving my liquid, working fluid, if you will, through a cycle, I can use it continuously over and over again. And the net result is going to be to take heat. I'm going to call heat my required input. And I want to produce work, which is my desired output. And in order to make a closed loop, in other words, a cycle that allows me to run my engine continuously, I probably need to remove heat, although I haven't really proven that that's true. But notice that I'm adding heat, right? I'm adding heat. I'm producing work. And one of the questions we're trying to answer is, can the energy and heat be completely converted to work? If that were the case, then it would not be necessary to remove heat. And I think maybe it's a spoiler alert, we'll find that that is not possible. So we do need to remove heat, and this is a byproduct. And the question that Carnot was trying to answer is, how much useful work can we get by burning fuel which I'm going to call heat, Q hot. And we might consider, a more mathematical formulation. We may want to say we're really looking to evaluate what efficiency we can get. So I'm going to say efficiency eta equals the desired output in energy over the required input. And in this case, this is the output work divided by the input heat. Ideally, well, I'm not sure what ideal really is, but in some fantasy world, we would love to be able to take fuel and convert 100% of it into useful work. Let me make it a little more clear what useful work is. So what is useful work? At the time of Carnot, it was maybe before the Industrial Revolution or at the early stages of the Industrial Revolution, he was interested in things like steam engines, which give you propulsion. Propulsion could mean running a train or a boat. And that would be better than using things like sails to propel a sailboat or horses to propel a buggy. You could also produce work in machines related to industry, right? A factory. Now, these days, our modern concept of useful work is mostly electricity. So this is back in the day. And this is modern. Electricity. So heat engines are run at the power plant that provides electricity to run modern society. So you can use a dynamo or a turbine to convert useful work into electricity, and then you can use that to produce whatever you like. Maybe this is a little too modern, but you could use it to run an electric car by charging a battery. Now, Carnot had the following observations to help him. The first is that reversible processes maximize work production. In fact, I think Carnot was probably the person to prove that. I'm actually not going to prove that here. I'm just going to state it as fact. But what does reversible mean? So reversible in practical terms means vanishingly high, vanishingly small. Driving forces. And what I mean is sort of a delta T, like if I'm heating something up, I'm heating it with a fuel source or a heat source that has almost exactly the same temperature as the thing I'm trying to heat. So delta T is approximately 0. And if I'm trying to do work through a pressure difference, the delta P that I'm expanding against is approximately 0. Vanishingly small driving forces also make for very, very slow generation of work or power. But that also tends to be the limit at which we get the most output. The other thing that Carnot is credited with is sort of the early formulations of the second law of thermodynamics. I'm not going to prove this, but I'm just going to state it. The second law is that delta S of the universe, which is equal to delta S of the surroundings, plus delta S of a system, is going to be greater than or equal to 0, and that in a reversible case, delta S of the universe is equal to 0. What is entropy? Well, entropy, so what delta S, or let's actually use the differential form, ds, is defined as dq reversible over T, whatever temperature at which the heat transfer occurs. Now, reversible, what it means is that if you have, whether you have a reversible process or not, the entropy change of your system corresponds to some hypothetical reversible process that results in the initial and final state. Again, this is not something I'm going to delve into in a lot of rigor right now, but I'm going to use the concepts to analyze what is possible for a heat engine. So a Carnot engine is a fully reversible engine such that the delta S of the universe is equal to 0. The heat exchange occurs at roughly 0 temperature. Pressure-driven work occurs with very little delta P. Now, Carnot's engine can be described in many different ways, but the way I want to describe it is something that resembles a real process, even though real processes are not usually Carnot processes. The irreversibility is a fact of life. But I'm going to describe how one would actually build a something resembling a real heat engine, and we'll first treat it as if it's fully reversible. Let me show you what I mean. Okay, so how do I input heat? Remember, I've got to input heat by burning fuel, and I've got to convert that into work. Okay, I'm going to do that with a boiler. And I'm going to have a Q boiler. Again, this is my required input. And then notice that this is going to imply that when I go from state 1 to state 2, the input and output of my boiler, I'm going to say delta S 1 to 2 is going to equal QB over T boiler. I'm treating it as if it's a reversible process, so I'm going to assume, even though that may not be reality, that my fuel is being burned at a temperature T boiler, and that the fluid that goes through the boiler is also at almost exactly that temperature. It has to be slightly lower, but only infinitesimally lower, in order to accept the heat. My input is going to be a liquid at high pressure. We'll see why the pressure is high shortly. And I'm going to output a high pressure gas. I boil the liquid. Now that I have a high pressure gas, I can extract work from it with a turbine. And I'm going to call it negative WST. Now there's a sign convention that I'm going to stick to. I'm going to treat the fluid that is running this engine as my system, and the entropy changes are going to be related to the system, right? So I'm going to say positive delta S12 corresponds to heat input, meaning that it increases the entropy of the boiler. Now the turbine is outputting work, right? Which means the system is going to lower energy, or is going to have lower energy because of the turbine. So I'm going to treat that work output as negative because it's work that comes out of the system. So it's going to lower the energy of the system, and this is our desired output. Okay, now state 3 is going to be a low pressure gas. Because it has undergone expansion in order to produce work by turning the turbine. And now what I'm going to do is I'm going to use a condenser, and I'm going to extract negative sign QC, which I'm going to reject into the environment. And my delta S of 3,2 is going to be negative QC over TC, meaning the entropy of my fluid is going to decrease because I'm taking entropy out of it. And finally, to close the loop, I'm going to use a pump. So this is state 4. Let me redraw this line. And in order to go from a liquid at low pressure to a liquid at high pressure, I need to use a pump and I need to input work. And I'm going to assume that this work is supplied by the turbine. I don't have to supply it by the turbine. I could just pump or plug the pump into the wall. But I'm just going to assume for my efficiency formulation that I have to pay for the pump with the turbine. So the efficiency here, as drawn, is going to be your desired output over the required input and so my required input, I'm going to say, refine what I said earlier and say that this is the output work from the turbine, but I'm actually going to offset it by the work of the pump. And my required input is QH. Notice that QC is not in the is not in the equation for efficiency because it's an output, but it's not a desired output. It turns out it's necessary. And part of what we're doing here is to understand why it's necessary. I'm going to go into more detail in the next videos, but let me just make a few comments. I want to talk about practicality versus conceptual understanding. Carnot's analysis is actually mainly intended for conceptual understanding, but I feel like it's better to use something that resembles a practical process in order to get that conceptual understanding across. And so, you know, there's a trade-off here, and that is that sometimes reality gets in the way of understanding. So if we dwell too much on how real processes work, we may lose sight of what is theoretically possible. However, if we dwell too much on what is theoretically possible, we talk about a system that makes no sense, like students can't picture it. So let's try to draw a balance between those, and so let's recognize that, okay, water is normally the working fluid. Water is readily accessible to power plants, and for cost reasons, you usually use water. Now, so too much abstraction alienates learners. For example, ideal gas, which is often described in textbooks as the Carnot working fluid, is weird. So I'm going to stick with water. And before I end this video, I'm going to draw things on a temperature enthalpy diagram. So if I plot temperature versus entropy, I think I may have said enthalpy earlier, I meant entropy. And I'm going to draw this on the two-phase envelope where this is the critical point. These are my states. Okay, so state 1 is what goes into the boiler. This is state 2, what comes out of the boiler. I'm going to assume the turbine, by the way, this is liquid, this is vapor, this envelope is liquid plus vapor. I'm going to assume the turbine is isentropic. That's actually not perfectly practical. And by the way, I'm also assuming that the turbine works in the fluid that goes through the turbine is a mixture of liquid and vapor, which is also not so practical. We'll talk about how to modify that for reality later. I'm going to assume the condenser produces... It takes in a mixture of liquid and vapor, and it outputs a mixture of liquid and vapor such that state 4 has the same entropy as state 1, so that the pump can also be isentropic. I'll explain more detail later, but I think the boiler and condenser are actually reasonably practical. So by working in the two-phase region, you have a well-defined boiling temperature at the given pressure of the unit, and so you can probably realistically assume that temperature is constant for the boiler and condenser, although not the same temperature. Let's say this is going to be TB, this is going to be TC, and however, it actually isn't very practical to operate a turbine or a pump with mixtures of liquid and vapor. But I'm going to live with that for the moment so that we can discuss the Carnot efficiency. And before I put it together, I'm going to have a little more detailed discussion about what ideal behavior is for the thermal and mechanical units in my process.